So let us recall what we have did in the previous lecture. In this previous lecture, we have talked about the homeomorphic spaces. That is, if x1 and x2 are called the homeomorphic spaces, if there exists some map which is 1 1 onto plus it is continuous and f inverse is also continuous, then we can say that f1 and this x1 and x2 are homeomorphic spaces, and a map f, it's called the homeomorphism. We have proved that under the homeomorphism, the every open subset of x1 will send image will be also open in x2. That means A is open in x1 will implies that f of A is open in x2. So if you remove this condition of inverse is continuous, will not be, this statement will not be true. A same statement we have proved for closed also. Then we have defined a closed map and open map. The closed map is a map which satisfying this condition, which we have A is open implies f of A is open. A closed map will have the same. And we have seen that there is a relation between the homeomorphism and open map, which tells you that the homeomorphism double implies continuous plus open map. So any homeomorphism is a continuous plus open map, that we have proved. Then we have talked about the isometry. So there will be isometry between two spaces if there is a map which is satisfying or it can be having the distance preserving. That means for every x1 and x2 in x1, we will have this distance will be preserved, and it's called the isometry. We have proved that this isometry implies 1 1, and we have also seen that if isometry is onto, then f will be a homeomorphism between these two spaces. And then we have talked a lot examples based on this homeomorphism. In this lecture, we are going to discuss regarding the totally bounded set. So probably in your previous studies, you have studied regarding the bounded set. Here, our discussion is based on totally bounded set. So there is a difference between bounded set and totally bounded. A bounded set means whose diameter, suppose say that I want to say that A is bounded set, then its diameter is bounded. If the diameter is bounded or it is a finite number, then we can say that A is a bounded set. Here the definition is about the totally bounded set. So for that I required one metric space. Let x comma d be a metric space. A subset of x is said to be totally bounded if for given epsilon greater than 0 there exists a finite number of subsets, let's say that subsets are a1, a2 up to an of x, such that or with this diameter of each of these subsets is less than epsilon for every I running from 1 to n. So I should not write such that here So with this, such that the A is covered by this union of the sets. So it says that it's covered by this union of AI whose diameter is finite. Okay. So I can say that A is covered by union of this A1, A2 up to AN, where each of them is having the diameter finite for given epsilon. So obviously now there will be two term is there. The one is bounded set and another one is totally bounded set. So which one is implies which? What is your opinion regarding this? That means I have a totally bounded set on the one side. On the other side we have a bounded set. So what will be the relation between totally bounded set and bounded set? When can I say that totally bounded set implies bounded set or bounded set is implies totally bounded set? Bounded set we have seen that it is a diameter is finite. Here it says that your A should be covered by some AIs where each AI is finite or it having a diameter is less than epsilon for given epsilon. If I give you epsilon, according to that you can able to find out each AN and it will cover this A. That is the definition of totally bounded set. So which one implies which one? Whether this is true or this one is true. That means every totally bounded set is bounded or a bounded set is totally bounded. What is your opinion regarding this?
A totally bounded set is bounded set.
Yeah. So that is the things you are right that every totally bounded set is a bounded set. Let us try to prove that. So see this side is not true. That we will give example for counter example for this side. The first objective is to prove that every totally bounded set is a bounded set. So if the subset A of a metric space x comma d is totally bounded, then prove that A is bounded. Bounded means the diameter is finite. That we need to prove. So here we have to show that A is bounded. So it is sufficient to prove that a diameter is finite, or I can say for every point xy in A whose diameter or the distance between that two points is finite. So proof for that, we shall show that A is bounded. It is sufficient to prove that for every point x and y in A, d of xy is finite. That is our objective. We will prove this. Now given that this A is totally bounded, so there exists some, or for given epsilon greater than 0, given that A is totally bounded, So for given, so I will choose that epsilon is equal to 1, and there exists a subsets. There are finite subsets or finite number of subsets, that is a1, a2 up to an of x, with the diameter of each of this ai's will be less than 1, because we have taken epsilon is 1 for every I running from 1 to n, such that A will be a subset of union of each of this ai. That means A is covered by this. This is because of A is totally bounded. Now let us choose arbitrary point AK in each of this AK for every K running from 1 to n. So there are some sets which covered this set A, and so this is the situation. Suppose this is A and this AIs are subset of X, so it will having such situation like this. Okay, so I am picking up one A1 from this set, A2 from this set, A3 from this set, A3, or and so on. Now I'll take this any and make some space here. I will fill up this space later on, because I want to set how to prove that this d of xy is finite number. So that means there exists some m, and what is that value of m, that I will write down here. So take any xy belongs to A. Therefore, this x and y belongs to union of this ai due to this equation 1. So that means this x and y are in some of these ai's, and maybe they are in this separate set. So I can say that therefore x is in ai and y is in aj for some ij from 1 to n. So from this we can have this. Without loss of generality, we assume that I is less than j, because I and j are integers from 1 to n. So without loss of generality, I may assume I is less than j. And let us choose each ai belongs to ai, that we have already did it earlier. That is each ai. Let us choose this ai is in ai. Okay. Now I will have this distance d of xy. As per the triangle inequality, we can say that this is less than or equal to distance between x and ai plus ai plus 1, sorry, ai and ai plus 1 plus ai plus 1 to ai plus 2 up to so on d of aj comma y, because I is less than j, so that's why we are adding this. So by triangle inequality, so I can say by triangle inequality we have this. Now further you can say that this x is in ai and this ai is in ai, So what will be the value of this 2? Due to the diameter of each of AIs is less than 1. So that's why this will be less than 1, this is less than 1, and rest of the quantity will be the same. So I can say this is less than 1 plus d of AI plus 1, d of AI plus 1, AI plus 2, up to what will be the previous term to this, that is d of Aj minus I Aj plus 1. So this is 2 plus, so that will be 2 plus. Now I am adding further more terms into this, so that's why I have written less than. So I am just adding these terms A1, A2 plus d of A2, A3 up to so on d of AI plus 1 up to so on d of Aj minus 1 Aj plus I am adding further more terms here plus d of A n minus 1 an. So I have added this terms, this many terms I have added from here to this, and all of them are positive numbers. So that's why I can write down that is less than this quantity. And I may call this is the quantity which is as m. So in the previously I am just writing here, that is take m equal to d of a1 a2 up to, or d of a2 a3 up to d of an minus 1 an. So that's choose here to make that constant fixed number. So therefore from this now we can say that d of xy is less than 2 plus m. This is because of star. What is star? Is we can write down that is the star, that is our assumption. And this is true for every point xy in A. So therefore we can say that A is bounded. Now converse of this result will not be true. That we need to prove by an example. So that is as a note I can write here. The converse of above result is not true. It is not true. For example, I can consider L2 space. What is L2 space? Let us define first what is L2 space. L2 space is set of all sequences, that is xn, which is I can say x1, x2 up to so on. So it is a set of sequences, but it is a square summable sequences. So it is says that summation I running from 1 to infinitive mode of xi square whole raised to 1 by 2 is finite. Or I can say if I don't want to write down the square root, and also it's fine. We can write down that it is a square summable, then it is also. So this is your L2 space. This way we define L2 space. So, and one can prove that this L2 space is a metric space. If you define your metric, that is xn, yn, if you define like summation I running from 1 to n mode of xi minus yi square whole raised to 1 by 2. If you define your metric like this for any xn, yn belongs to this L2, then this space L2 is a matrix space that you can prove easily. So that I am giving you as an exercise to prove. So check that L2 is a matrix space with this matrix D. It is usually called D2 space or D2 matrix because it is a square. And you can generalize this definition with the P norm or power P, where P is greater than or equal to 1. You can generalize this definition for that also. And I will tell you that this example which I am discussing is one times asked in the net exam also. That is, if I define E1 now, so E1 I am defining as 1 0 0 0 and so on. E2 is 0 1 0 0 0. So in general, En is I am defining in such a manner that this 1 you will have at the nth place and all the rest of the entry are 0. This is n at the nth place. Okay, so that is our En. When I am defining a set A, which is E1, E2, so it's consisting of this En set. These are the E1, E2, E3. So is this A is a subset of the L2 space, that is we need to prove first. Okay. So what is this? I can write this A as this one also, that is En, which is 0 0 1 up to 0 and n belongs to n. This is also can be right. What is the summation of all of them? As it is obvious that this A is a subset of L2 because what will be the summation? So here in this case, if you want that any element it is in L2 or any sequence is it in L2, that means that has to be square summable. So here the summation of all this 0 square plus 0 square plus 1 square up to 1 square. So this summation of I running from 1 to infinitive mod of xi square, in this case it is 1 and which is already finite. So therefore I can say that this A is a subset of L2 and this is true for any n. So it will be a subset of L2. Now our objective is to prove that A is bounded but it is not totally bounded. So we shall prove that A is bounded but A is not totally bounded, and which is the converse of that result, that is totally bounded implies boundedness, but boundedness does not imply totally boundedness. That is, this things is there. Now if I want to prove that it is bounded, then I have to prove that every pair of points in this will have a distance finite. So for that, let us take this EI and EJ belongs to A for I, for some, or for any ij in natural number n. Then what will be the distance between EI and EJ? As per I told you that the metric which I have to use is this metric, that is summation I running from 1 to infinity. Here it is infinity mod of xi minus yi square raised to 1 by 2. So if I use that one here, that is summation k running from 1 to infinity mod of ei, I can say that is at the place k minus ej at the place k whole square whole power 1 by 2. Now what is this EI? We know that at the ith place it will gives me one answer, and all other places it will have a 0. For this EJ, for the jth place it has one answer or one value, and all other places it is 0. So it is the kind of the things we have like this: 0, 0, 1. This is at ith place. And if I assume that I is less than j, then you will have and I'm assuming that I is not equal to j. If it is equal to j, then what we will have, let us see, let us talk about that also. So here at this place, ith place, it will be have a 0, and at the jth place we'll have a 1, and so on. So this is the jth place, and this will be the ith place. So ei minus, so the subtraction of this two will gives me 1 minus 0 at this place, plus somewhere it is 0 minus 1, and the square is already there. Square is there. That is square of that. So it will gives me, if I is not equal to j, it will gives me 1 plus 1 square whole raised to, sorry, 1, not 1 plus 1 square, 1 plus 1 minus 0 square and 0 minus 1 square. So it gives me 1 plus 1 whole raised to 1 by 2. So that will gives me square root of 2 if I is not equal to j. If I equal to j, that means this is at the same place. This 1 is at the same place. So in that case, this is also 0. So in that case, it will gives me 0 answer. So that means, therefore, what I can say in general, di minus dj is equal to root 2 if I is not equal to j, and 0 if I equal to j. So what we can say that from this, that diameter of this A will be a supremum of distance between each EI, EJ, where EI and EJ for every I and J belongs to N. What is EI, EJ? We already defined earlier. But supremum of this distance is root 2. That will be two possibilities, 0 or root 2. So the supremum distance is root 2. So the diameter is bounded. So we can say that, or diameter is finite. So we can say that A is a bounded set. Now we have to prove that A is not totally bounded. So for that I am taking, that means A cannot be covered by a finite number of AIs, which are the subsets of A or X. X is L2 here. So we have to prove that does not exist any of this finite number of AIs which cover this set A. That is our objective. So for that I am taking X or epsilon is equal to 1. I am taking epsilon is 1. And I am defining one set that is a sphere of EI with radius 1 by 2. So it says that the set of all xn in A such that a distance between xn and EI is less than 1 by 2. So as per the definition, this xn is EJ, so this is only having one point because of distance between EI and EJ is equal to root 2 if I is not equal to j, equal to 0 if I is equal to j. So only one possibility is there. Okay, so that is the sphere of radius 1 by 2 will have this EI, only one set. That means what I can say, therefore, the only non-empty subset of A with a diameter less than 1 are singleton elements. So any non-empty subset of A due to this will be a singleton element in this set. But your A is infinite set because A contains infinitely many points, E1, E2 up to so on. So we note that A is infinite. And hence this A cannot be covered or cannot be written as union of finite number of distinct subsets of distinct subset with a diameter less than 1. And therefore we can say that A is not totally bounded. So ultimately what is that things we have done here, that A cannot be covered with the finite number of singleton sets because we have taken the diameter is less than 1. So here these are the sets which cannot be covered entire set A because these are the singleton set, and singleton finitely many singleton set will not cover infinite set. So that's why this A is not totally bounded. So this is one of the example regarding this statement that totally bounded implies bounded, but the converse is not true. There is another example is also there which gives you with the discrete metric space we can have. This is another example, the example 2. So let X be an infinite set with a discrete metric. Discrete metric means d of xy is 1 if x is not equal to y, 0 if x is equal to y. That we know. Then prove that x is bounded with respect to the discrete metric but it is not totally bounded but x is not totally bounded with this map or with this metric. Again with the same argument we have did it earlier. That means let us take this epsilon is 1. Then the set S1 by 2 x. So this is open sphere. It is set of all y such that distance between x and y is less than 1 by 2. But we have taken this epsilon is 1 and the radius, so this distance x1 according to this definition, that is if x is not equal to y, it has to be 1 or 0. Since this radius is less than 1 by 2, only one possibility is left here, that is this distance has to be 0, so that's why this x is equal to y. So that only the center will be there. Okay, so this is the things we can have. The set will only contain singleton point. Now the non-empty subsets of x of this, the diameter less than 1 by 2 I can say, or less than 1 are singleton subsets. So that is the statement we can write. Therefore, the only non-empty subsets of x with a diameter less than 1 are singleton subsets. They are the singleton subsets. Now since x is infinite, x cannot be covered with finitely many points. Okay, it cannot be covered by finitely many points. So therefore x's are not totally bounded. So that we can write, since x is infinite, because that is given, that we have taken. Since x is infinite, set x cannot be written as the union of a finite number of sets of diameter less than 1. Hence, the infinite set x with discrete metric is not totally bounded. Okay, so any map or any set, you can say infinite set, you can write down closed interval AB with a discrete metric. It is not totally bounded, but it is bounded because its length, its diameter is b minus a. Okay, so here I should clarify that when prove that x is a bounded, that is not correct statement, because if I consider R, then R will not be a bounded set, but it is not totally bounded with the discrete metric, that we can say. So I think so this statement I should not write here, that prove that, and I can say and x is a totally bounded with respect to discrete matrix bit, but prove that x is not totally bounded. Let's next change statement like this. Now there are certain results on this totally bounded set we have. The result says that if A is totally bounded, can we say about its closure is also totally bounded? That is the next theorem. Regarding A is totally bounded, can we say its closure is also totally bounded? The first observation that you can make is A is totally bounded and B is a subset of A, then it will implies B is Totally bounded or not? What is, whether this statement is true or not? What is your opinion regarding this?
Yes, sir, it is true.
It is true, but because those sets which are covered A, the same set will work for B. Okay, so if A is a subset of, sorry, B is a subset of A and A is totally bounded, then B is also totally bounded. We have a next result is if A is totally bounded, subset of a matrix space X comma D, then prove that A closure is also totally bounded. So closure of a set is also totally bounded. That is the objective of the next result. So let us try to prove this. Given that A is totally bounded, so as per the definition of totally bounded set, for every given or for given epsilon greater than 0, there exists a finite number of subsets AI of X with each of them having the diameter less than epsilon for every I running from 1 to n, such that A is covered by this AIs. Now we have already proved that if A is a subset of B, we already did this. A is subset of B will implies that A bar is a subset of B bar, which we already have done in previous one of the lecture. So according to that, we can say that this A closure is a subset of a closure of this. So A closure is a subset of union of this A closure. We already also proved that A union B closure is a subset of A closure union B closure. So as per this, we can write this is subset of, since this is a finite union, so we can write down this is the things. Now I am giving you one exercise here to prove that if the diameter of A and its closure will be the same, the diameter of the set A and its closure will be the same. That you can do it in exercise, or those who want to do the presentation with the similar kind of result. There are 2-3 results of such kind which is given into the Das and Patnaik book. You can go through it. There are similar type of results are there. So those who want to do the presentation on this, they can do it. So now also note that we can here, I am giving you as an exercise to do this, that each of this diameter of each of this, you can prove, check is true. So what we can have, the diameter is same, so I can say that A is covered by a finite number of AIs whose diameter is less than epsilon. So therefore A closure is totally bound. So closure of a set is a totally bounded. Now we have a very important result actually, which gives you this regarding a relation between a totally bounded set and the sequence. Okay, so that is actually this result is if and only. The converse part one can do it in the project. Here I am proving only one side. That is, let x comma d be a matrix space and a subset A of x is totally bounded. Then prove that every sequence of points of A contains Cauchy sequence. That means if you consider any sequence of A will contain a Cauchy sequence. This result is actually a if and only if result that I am saying. So instead of this then, I may also write down if and only if. That means every sequence of points in A contains a Cauchy sequence, that will imply A is totally bounded. This result is if and only if. But here I am proving only for one side. Those who interested, they can try to prove the converse side and they can do it in project. Okay, that means they can prove that every sequence of points in A contains a Cauchy sequence, implies that A is totally bounded. So let us try to prove this here. So let A is totally bounded. It is given. That is our assumption. And here I have to prove that every sequence of points in A contains a Cauchy sequence. So I will start with let xn be a sequence of points in A. So A is a sequence in A. What is our objective? We will show that, or we shall show that the sequence xn has Cauchy sequence. That is our objective. So since this A is totally bounded, for given epsilon greater than 0, there exists AI which are the subset of X with the diameter of each of this AI is less than 1 for every I running from 1 to n. So there are finite number of this AI such that A is the union of this AIs. Where diameter of AI is finite, that I will read it. Now this xn, it is in A. Will implies that xn is in union of this A. Now it may possible that this each of this an, so there are infinitely many points of this an will contain in some of this AI. If suppose that otherwise the sequence will be finite. If I can say that each finite element of this an will be containing AI and each AI are finite numbers. They are finitely many sets. So A1, if A1 contains finitely member of xn, A2 contains finitely member of xn, and so on. An contains finitely many members of xn. then this xn sequence is itself a finite sequence, and every finite sequence will already have a Cauchy sequence. Okay? So this sequence is infinite sequence. So that means one of this set A1, A2 up to An contains infinitely many points of this xn. Let us say that set is A1. Okay. So therefore what we can say, one of this set, let's say A1, let us say that is A1, will contain infinitely many elements of the sequence xn. So this A1 contains infinitely many points of xn. Otherwise, the sequence will be a finite sequence. Okay, this will be a finite sequence. Let us choose one element which belongs to A1 and call it xn1. So there are infinitely many points which are in A1. So choose element belonging to this A1 and call it xn1. Now A1 is a subset of A. Or some part of A1 will be a subset of A. And A1 is a totally bounded, because A is totally bounded. Because subset of a totally bounded set is totally bounded. That means this A1 is covered by finitely many subsets. So therefore it can be covered by a finite number of subsets of A of diameter less than 1 by 2. I am taking a diameter will be less than 1 by 2. Let us consider, or let us say that set, let one of the set, let's say A2, must contain xn for infinitely many. And again with the same argument, if it is contains a finitely many elements, then each of that set contains a finite, then it will not be possible. So let us consider this A1, this A2 contains infinitely many points of xn. Let n2 is greater than n1 such that xn2 belongs to A2. And since this A2 is a subset of A1, this xn2 is also belongs to A1. And proceeding in this manner, that means in this manner if you proceed after n step or after k steps, so proceeding in this manner for any k belongs to n, we can find a subset ak of ak minus 1 with diameter ak which is less than 1 by k, and the term x and k is belongs to a and k of the sequence xn. So every time we will have such things. Since this xn k, xn k plus 1, xn k plus 2, all of them is belongs to ak with a diameter of ak is less than 1 by k, I can say that this xn k is a Cauchy sequence in A. So as I told you, this result is if and only. Here we have proved that A is totally bounded if and only if, or then every sequence has contains a Cauchy sequence. The next result, it tells you regarding the totally boundedness and the boundedness is same into the usual metric space in a real line. So in the real line, A is totally bounded stopping. So in R, if A is bounded, then it is totally bound. Totally bounded always implies boundedness. The converse is not true, that we have done with the L2 space. But in R, if any bounded set is there, then it is automatically totally bounded. That can be proved by the previous theorem which we have did, and using the Bolzano-Weierstrass theorem which you have already studied in your previous semester. What happened? It's not showing. Something is wrong here.